So an elementary matrix is a matrix that comes from the identity by one row operation. Okay, so we have three kinds of row operations, so that means that there's three kinds of elementary matrices. So it's easiest just to show what these look like by examples. So suppose E1, let's do some 3x3s. We have 0, 1, 0, 1, 0, 0, 0, 0, 1. So this comes from the identity by a row swap, where we've just swapped the first two rows right here. One of the other row operations that we have is we can scalar multiply by a constant. So for instance, this one right here, I've multiplied the third row by 3. And for the last type of row operation, where we add a multiple of one row to another row, let's see, so if we start with the identity matrix, and then we add 2 times row 3 to row 1, we'd get a 2 here, and everything else would still be a 0. So here's examples of the three basic types of elementary matrices. So an interesting and curious thing is the following observation. So if you recall, we had a homework problem that asked, what happens if you multiply by a diagonal matrix? And the answer was, each row gets multiplied, scalar multiplied, by the corresponding entry on the diagonal, right? At least if you put it on the left. So the observation here and sort of generalizes that. So if you multiply by putting E2 on the left of a matrix, it will multiply the third row of that matrix by 3. And so more generally, the same thing holds. So if an elementary matrix E comes from the identity by row operation R, then when you multiply E on the left side of A, it does that same row operation to A. So EA comes from A by the same row operation. Okay, so maybe I should just emphasize that, right, that EA is row equivalent to A, and it's row equivalent by the same row operation that was used to create E in the first place. So what that means then is that, actually here, let's not call this a definition, let's call it a proposition. So proposition. A is row equivalent to B if and only if there is a sequence of row operations that takes A to B, right? Well, now we know that row operations can be implemented by multiplying by elementary matrices. So A is row equivalent to B if and only if there is a sequence of elementary matrices. Such that, and so if we start with A and we multiply it by the first elementary matrix E1 and then the next elementary matrix E2 and then keep on doing that with a whole bunch of elementary matrices, eventually we end up that this is actually B, because that's the same thing as saying that we do start with A and then we do some row operation to get some other matrix A1, which is actually E1 times A, and then we do some other row operation R2 to get some new matrix A2, which is actually E2 times E1 times A, and so on and so forth, lots more row operations until eventually we get to B. Okay. And we have a couple of observations that follow on the tail of this. So, theorem. If E is elementary, then it is invertible. And its inverse is elementary and of the same type. Okay, so now why should this be? Well, turns out this is the simplest thing ever. It just has to do with the fact that row operations can be undone. And that's it. Now, to understand why that's the proof, notice that A comes from the identity by, E comes from the identity by one row operation, right? So in other words, we have this identity, and it takes one row operation to get from I to E. So then we can go back to the identity by just doing the opposite row operation. And the opposite row operation is going to be an element. There's going to be an elementary matrix that corresponds to that. And if I write that elementary matrix next to the first one, it's going to cancel out and take me back to the identity.